Yeah, I'll wait a second. So we're just discussing the interoperability that we discussed in the RCast for this week. And so one thing that I've been thinking about since that conversation is, and so like I was saying, I don't know if you guys got to this point in the RCast, but he's talking about interoperability with the Bitcoin blockchain. And essentially, well, my understanding of it is that he's saying we can kind of like import, some information from the Bitcoin blockchain as like a certain special class of names into, rolling, and then we can kind of interact with it there. But I don't know how we do the actual logic and the consensus from the Bitcoin blockchain, and how that maps onto like the consensus that we have for the R chain. So I don't know if you guys have any thoughts on that. How's it going, Peter?
Hey, Peter.
Hey, Peter. I think he starts on that pretty early. And
Yeah.
Brings up a couple of points, but the main point is, the trust.
Yeah.
We trust the Bitcoin network.
Right.
We only look at the inputs and outputs.
Mm-hmm.
Okay, we're not concerned with other aspects.
Yeah, that's right. So we're not concerned with the consensus mechanism. We kind of take it as this is what they came to consensus on. Okay, great. We record it on our chain or whatever.
Right.
Yeah.
Now
We were
you can also have a global consensus or a consensus among blockchains. Okay, which is dealing with things, a namespace that's shared between the blockchains. Okay,
Yeah.
that's where you have to have that sharding, bifurcation or whatever that is talking about, like a Unix file system.
Mm-hmm.
Okay, of namespaces.
Yeah.
Which are hierarchical spaces like the web. Everybody's using GUIDs, flat address systems.
Mm-hmm.
And ultimately, that's wrong. Organization, structure.
You're saying because they should be hierarchical?
Well, it needs to be structured.
Yeah, structured. Okay. Right.
So how does our chain talk about reaching consensus across different blockchains? Or do they?
Well,
yeah, so, you can go ahead, Jim.
Yeah, the more global consensus that you want, okay, the slower you're going to be.
Mm-hmm.
The stakes are going to be higher. He just characterized it basically that local consensus is fast, and global consensus is
Future.
Yeah, you have to get, in order to get, when you have multiple blockchains, okay, you have to sort of think of the other blockchains as actors,
Mm-hmm.
and use multi-phase commits to enforce the process calculus.
Yeah, I was looking through Parody's Grandpa again and just like realizing what that finality gadget is intended for, really to cross the bridge between existing chains.
Yeah, that's very cool the way that works. It seems to be sufficient. And, you know, that's the whole thing. You know, we have FLP and possibility. We know there's not going to be a perfect solution, but we want something that's good enough. And I guess what Bitcoin does is good enough there. And in the multi-chain arena, Grandpa may be good enough, okay, to do it. And, you know, we may have, you know, I think it ultimately has to be evolutionary. We have to keep improving on the algorithm. You know, Grandpa looks pretty nice for cross chain, and
yeah. So it seems like it's more for existing chains, which, you know, I still don't fully understand. Maybe Josh, you could even help us out with that if he's understood it better. But yeah, I am curious, you know, just how that compares with what our chain is thinking about namespaces, and if you could put existing blockchains into, you know, if they could like have their own name in this namespace and, you know, become part of the consensus.
Yeah, I haven't really looked at Grandpa since we did it back in May or whenever that was, so I don't know too much more, to be honest with you. But I would be happy to hear about it if you looked more into it. Or I didn't read would be the wrong word, but I skimmed the transcript of the last Rcast, and Isaac, I'd be interested in hearing what you guys were talking about there too.
Yeah. So the main takeaway that I got was so maybe I don't exactly know how Grandpa works, because in my mind, Grandpa is it only for like different parachains that want to, you know, communicate with one another, or is it just for any blockchain that's built and now you can like put this thing on top of it and have communication between like any blockchain you want, like the Bitcoin blockchain, for example?
I would say, you know, what Grandpa offers is finality.
Yeah.
It gives you that final piece of the puzzle by having rounds and being oriented, you know, you know, developing, you know, consensus among what people have seen. It's a voting mechanism, sort of.
Right. That sounds like the multi-phase commit you were just talking about.
Yeah.
Yeah, I had thought of Grandpa as being, yeah, like Jim said, like just a finality gadget, sort of analogous to like Casper FFG. So yeah, I'm curious, Jay, what were you reading? I mean, definitely it can be used like for Polkadot, where they're doing like the message passing and having the parachains and everything, but I know they also use it just in like the default substrate node where it doesn't necessarily have parachains or anything.
Okay, that makes sense. I did read it in the context of Polkadot. I was reading an introduction to Polkadot.
Oh yeah. Oh, interesting.
Yeah.
Which one was it? I try to read as many as I can just to make sure I'm up to speed on all of it, but there's so much.
I'm not sure. It was the one on Medium. I think it's one of their biggest posts.
Oh yeah, was it like Rob Habermeyer? It had the like minion looking diagrams. Yeah,
exactly.
I've seen that one.
Yeah. So okay, that makes a lot more sense, because when we were studying it, it seemed like as a consensus algorithm, we had never really talked about it as a finality gadget. So yeah, I was wondering, I was like, how does it seem so much like a consensus algorithm, but somehow it's also this finality gadget?
I mean, it is useful by itself, okay? But when we're talking about cross-chain consensus, okay, what we need, you know, in that case, we're using it as a finality gadget. In other words, we have these conflicting ideas on different chains, and Grandpa gives them finality. Okay. So it's solving disputes between chains at the higher level when you're using it, when you're not using it as your primary consensus mechanism, which we certainly can do, and will and do when we're running substrate. We're running grandpa as our only consensus mechanism, right?
Just with the voting, and there's no. So I mean, I guess is the criteria, if it is working as a finality gadget, that all the existing validators, say they're like proof of work validators, anybody that might propose a block needs to also be voting in the finality gadget?
If it's cooperating with other chains, yes.
Yeah, the way they set it up is that they use grandpa just for finality, and then they totally abstract away the concept of block production. And so they need not, like, in general, they need not be the same, like, voters or participants in the block production that they are in the finality, although in practice, a lot of times that is the same set, or at least, like, significantly overlapping sets. So it could be that you have, for block production, you know, something where you have some set of authorities that's making blocks, or it could be something like totally permissionless, like proof of work, where you don't even necessarily have to have a known set of authorities. But then with grandpa, you still do have to have some known, like, voter set, so that you can do your, like, you know, 2/3 honest majority and that kind of stuff. And then so grandpa just takes in, like, oh, here's another block on the chain. So it has this, like, view of some chain or DAG or whatever it is you're trying to come to consensus over, but it's not creating that thing. It's just like, oh, I just heard of another block, you know, and then I vote whether I want it to be, like, final or not based on what I've seen.
Mm.
And then my thought is, like, in Polkadot, so with Polkadot, when you have this multi-chain thing, basically you have, like, the relay chain and then all of these parachains around it. And so the kinds of transactions that you can submit to the parachain are like, I saw this block in such and such parachain, or I saw some other block in such and such parachain, and then those things go in via reference, like to a block hash, into the parachain's blockchain. And then if they become finalized in the parachain, then part of the, oh, sorry, wait, I think I swapped some vocab. Like these blocks from individual parachains go into, via reference, the relay chain. And if they're finalized in the relay chain, then part of the logic in the, like, parachains is like, okay, once it's finalized up in Polkadot in relay chain, then it's also finalized here.
Mm.
So grandpa itself is, like, kind of agnostic over whether the parachains exist or not. It's just coming to finality on, you know, whatever chain it is. In Polkadot's case, that's the relay chain. And then because the relay chain references parachain blocks, then they can say, okay, well, we're finalized too.
I mean, maybe I'm just confusing concepts, but this sounds a lot like sharding and kind of just having, like, a different hierarchy of these different, like, child chains where the child chains are like, you know, the parachains, and maybe there's, like, one main observer that's the relay chain, basically.
Yeah, totally. It's like, it's a super structured, it's a really highly structured, like, this is the prescribed roles of everybody and this is how we work together kind of way to do it, where there's, like, the relay chain and there's some known set of parachains. But I thought, well, and then Isaac, this is where I'm curious to hear, like, what you guys talked about, because I thought our chain solution was, like, a little bit more general than that, where there didn't have to be, like, one relay chain, where it could just be, like, two peer chains that happen to, like, have some interaction between each other or something like that.
Yeah, I mean, from what I know, it's more just like a tree structure of namespaces, and then basically it's like, you know, parents, you know, observes the any, you know, derivative of it, and, you know, they have this mint contract that kind of, like, is some sort of, like, resource binding between the parent and child. And you know, my understanding is, like, you want to be lower in this tree so that you can kind of, like, process transactions faster. You have less things to kind of, like, worry about and pay attention to. But you also have some incentive to be higher in the tree because there's more security when there's more observers, and, you know, you're dealing with more data. So yeah, I mean, I think it's as general as that. It can be basically any kind of tree structure that you want.
And, you know, two branches that are independent, okay,
Mhm.
may have, if they have a bit of reference that's overlapping, now they have to come to consensus between them,
Mhm.
okay? And that's, so it's like sharding, it's like, you know, uh, uh, and it's like ordinary consensus, but
Mhm.
the, uh, I think the key thing is idea is looking at it as namespaces and considering uh, just input outputs.
Can you talk more about that binding contract between an upper and lower level?
Yeah, I think they call it a mint contract. So it's just so that the parent namespace above the child namespace has some sort of reference to like what resources are being used, or rather, sorry, you create the child namespace from the parent namespace, so you're inherently using some resources in that parent namespace. So you just want to keep track of like what resources are being used in that child namespace. That's how I understand it, at least.
Hmm. So minting is in the sense that the parent is basically like minting and allocating some tokens for a child to spawn.
Right. Yeah. Exactly.
Hmm. Okay. And there could be collateral in the sense like you could you create tokens at the newer level that aren't necessarily the rock and collateralize them with rock?
Um, I'm not 100% sure how that works.
Yeah, this kind of gets into the token economics, but
Yeah.
Well, where the token is different, the cross chain kicks in. Okay, so now you can have two R-chain shards, which are actually forks if they don't use the same token. But these forks can have contracts between each other, so
Mhm.
they can work together. And in fact, this is the model that I'm looking for with the social ledger, is where everybody has their own chain.
Mhm.
Okay, and then if I communicate with you, we have a link in our chain that's common. Okay,
Mhm.
and we build the structure. Uh, uh, um, no, the skeleton of the social structure and our tools and everything that way.
hmm.
But what was my point?
That structure sounds a little bit like hashcraph. The way each person has their own I wouldn't necessarily call it a chain, but their own like timeline with their own events that they receive from other people.
Mhm. Yeah, I think that's kind of how C Delta or Casanova worked as well.
Hmm.
So Isaac, I remember from like months or maybe even a year ago, the idea of like tree-based sharding. And I was thinking I don't know why, probably because I only skimmed it, but I was thinking for some reason you guys were talking about like a more general thing where you didn't have to have like a strict set of like ancestors and everything, but I probably just misread it.
Yeah, I'm honestly not sure where that discussion is in its evolution right now. Like I know they were talking about like the lattice structure and there were certain undesirable things about the lattice structure that they wanted to avoid. And then they were talking about the tree structure, and honestly, I haven't really looked at it since the time that you're referring to.
Yeah,
So
yeah,
yeah.
yeah, cool. Jay, I think I can talk about their like collateralization process a little bit though. So I remember that because there's this concept of well, when you have the like prescribed tree structure, then it gives you this like pretty clear notion of like the root shard, or like the parent of all, well, yeah, like the root of the tree basically.
Yeah.
And so that's where like the native token just exists. And then when you want to mount a child shard on there, basically you like deploy a smart contract in the parent shard, whether that's the root or maybe you're like further down there, but whatever your parent shard is going to be, you deploy a smart contract that basically acts as a depository. So like I move some of the token into that depository and it's locked up. And then in the child shard, I have a mint contract that watches the depository contract in the parent shard. And so then it can mint some token that, if you're only looking at the child shard, it basically just looks like some new token. It doesn't have any relation otherwise. But if you zoom out and also see the parent shard, then you see that the token minted in the child shard is always fully collateralized by a token in the parent shard. And so when you have that like one-to-one collateralization, then you basically can brush the details under the rug for daily purposes and talk about it just being like the same token. So then if you want to move it back to the parent shard, then you just burn it in the child, and then the contract in the parent says like, okay, I see that the mint burned some token down there. Now I can release some of the collateral.
So that means that the parent has to be able to track all of its children and their consensus algorithms.
Yeah, exactly. Just like the relay chain does.
Oh, okay. Really? So the relay chain actually has to track. I thought it was just the other way around where So the relay chain has to track the parent chain and for finality, but the parent chain doesn't have to track a relay chain.
So the relay chain is the parent. Oh, it's weird because parent and para sound so similar. But yeah, the relay chain is the parent. Yeah.
Okay.
Yeah.
So you're saying the parent in parity actually does have to track the child.
Well, they in Polkadot they don't have that like collateral, that like depository and mint system, but in our chain they do. But the common theme there is that the parent or / relay chain has to be aware of what's happening in the child / para chain. So like in the Polkadot sense, which is where I know like more of the specifics, basically what happens is if a child chain has some block that they're trying to get put through, then the block header is sent up to the parachain and it's run through some checking function. And the parent chain doesn't necessarily know the specifics of the logic in the child chain, but what they know is that when this child chain became part of Polkadot, they were given a verification function. And that's all they know or care about. Like if the blocks pass this verification function, then they're considered good and we can go ahead and include them.
But it's not something that you could just call on one validator. The relay chain still has to be able to track like the consensus and the finality of each node on its own. It's not like there's a single node that they could query. Well, I guess you could generate a proof for whether a block is finalized or not, couldn't you?
Yeah, and so if you think of a shard as sort of another chain, a different chain, with maybe different staking, whatever, you can represent an asset on every chain. But in order to consume that asset, you have to coordinate with the other chains to actually get rid of it everywhere. Okay, so you have to have cooperative structure. So if I want to spend this, let's say, rev on Ethereum, or this representation of rev on Ethereum, it has to check. It has to. The transaction has to coordinate with our chains, so that make sure the rev is really there, or whatever.
Yeah, cross-chain communication like that, it definitely makes sense. But I'm just thinking, in terms of namespaces, if a certain node has a lot of children and they have to track each child, I'm just wondering if that tracking is basically an O of 1 operation where you can just query for a proof that a block is finalized, or whether you actually have to track the entire consensus mechanism of every children. And it would be the same
Yeah,
for,
and be like vote counting in every child and everything. You know?
yeah.
Ah, yeah.
Yeah, so one concept with Polkadot is that so Polkadot itself, the relay chain, has like some block production mechanism, which happens to be called Babe, and then it has Grandpa for finality. But in the parachains, you know, again, you have some block production mechanism, and I think a lot of them will use Babe, but it doesn't really matter. But your finality has to be Polkadot shared finality. So the in a parachain, the only notion of finality is this thing got finalized in the relay chain. So there's no like we came to finality over it here in our own little sovereign thing, and we hope also Polkadot comes to consensus over it. It's like we're delegating finality up to them.
Interesting. So what makes it its own chain? Why is it even considered like a?
Yeah. Well, that's a great question. Well, it has one thing that makes it its own chain is like literally the fact that its blocks have parents that reference, you know, like it has its own Genesis block and the tree or chain builds from there. Um, and so it like the parachains can have their own logic. So there could be one that's a currency that's like, you know, just Bitcoin where the kinds of transactions you can submit are like transfer these tokens, or one that's like just crypto kitties where the transactions are like transfer this kitty or breed these two or whatever. And that logic doesn't reside up on the relay chain. It only resides on this local chain. So then there's what they in the Polkadot world what they call collators, which are basically like validators who, like, let's say you submit a transaction to some parachain that says breed my two crypto kitties. So then the collators get that, they make sure that it's a valid according to the parachain's logic, and you know if not they throw it away, and if it is they're doing the block production thing, so it goes into the chain, and then they send it up to Polkadot in hopes that it'll get finalized in Polkadot, which then means by definition it's finalized for us down here in the parachain.
So is the relay chain in Polkadot, it exists just to kind of aggregate all of the parachains, right? And
Yeah.
to the finalization on all of them.
Yeah, exactly.
Okay.
So that, and they don't usually use the word concurrency, but like I like that word probably just because I come from our chain. But like you can think of, you know, each parachain is running its own block production mechanism at the same, well, concurrently.
Mm-hmm.
And so like these chains are being built, and so in terms of like avoiding total ordering, we don't necessarily need to know like did block A in parachain A come before block B in parachain B. All we need to know is like when did they get finalized relative to each other up in Polkadot.
Yeah, that makes sense.
Do you think that that's enough? Do you think that sharding on like this logical level is enough, or do you think that we do need this concurrency idea at like the actual smart contract level, like our chain?
Yeah, I mean, that's interesting. I think it's cool. I think it's a big step, and like I hope it works and everything. Like what I like about the way that Polkadot's doing it is that like it seems like the right size of step, where like it's something that seems like it's going to work and going to be a lot better than like what we've had in the past. But yeah, I don't think it's quite as cool as like what our chain has described at various points. But it's, you know, just that those things are hard to build and maybe the details aren't, you know, it doesn't seem like we're like right on the brink of just building it at that point.
Yeah.
It's almost as if we have to behaviorally, that execution becomes behavioral typing. That we actually search for we're searching for the algorithm that we're going to run, and you know, so you know, the query idea that these guys talking about is sort of seems like it's ultimately needs to be the execution mechanism.
Yeah, querying by behavioral type. It's a pretty cool idea.
Jay, you had a presentation yesterday on consensus, is that right?
Yeah, that's right.
How did
Hashcraph.
that-
Oh, cool.
Hashcraph.
Mhm.
How did it go?
Went very well. I can put the slides up in here if you'd like that.
Yeah, definitely. Where were you presenting?
Oh, it's just a local meetup here in Austin for hashcraph. I basically
Awesome.
just talked about the consensus algorithm, tried to like simplify it as much as I could. Got it down to 4 steps, a 4-step path to understanding consensus in hashgraph.
Nice.
Cool.
And
Yeah, what are the steps? Do you want to show us the slide? Do you want to present it again?
Yeah.
I mean, you guys know it now, I'm sure. I could
Don't overestimate my knowledge.
do a 5-minute piece on just that part.
That'd be cool.
Yeah, definitely.
Let me open it up. Yeah, Jim, you actually never uploaded last week's video.
I thought he did upload it. You're talking about Jim?
Mm-hmm. Yeah. I
I
didn't
thought
see
I
it.
saw it, but I could be wrong.
Okay, so all right, here's the slide. All right, so there's 4 steps, and I was using a diagram from the paper to explain them. Yeah. Okay, so the 4 steps to consensus in hashgraph are the first one is seeing, so the concept of seeing. An event season. Okay, and just a quick recap. Each line is through time. The top is the latest time, is the earliest time. Each line is a validator. And when we talk about consensus or finality and things, it's between events, not validators. So when we say that an event sees another event, it doesn't really have anything to do with a validator. Like an event can see its own self-parent, which is from the same validator. So the concept of seeing is just that an event is an ancestor of another event, and that it can be traced.
So if it's an ancestor, it's seen by the descendant, like the descendant sees the ancestor.
Yeah, exactly. And the higher nodes again are the ancestors of the lower nodes.
Yeah, I think the most confusing thing for me about hashgraph is it's all in terms of these events and not the validators, which is kind of what you're expecting to some extent.
Yeah, exactly. And that, I mean, is the interesting part too, because they fuse the networking protocol layer with the voting layer, so they become one thing. And
Yeah.
I mean, it really is just like an optimization. You no longer need to talk about the votes because it's built in. And
Yeah, that's a good way to look at it.
So Jay, I have a question about this too. When this is used, like we always kind of talk about it in the abstract, but if we use this to actually build some like consensus machine where there's like extrinsic calls coming in, like transfer 10 tokens to Jim or whatever, are those the payload that are associated with events, or do those go somewhere totally different?
yeah. So each event can have a payload or it cannot, either way. It's a maybe.
Okay. So like I could make events without a payload just to participate in hashcraph, but in as much as there are ever transactions coming in, those are the payloads of events.
Exactly. Yeah. So if you look at just some event, like this one sends or it has an outgoing event to another one and an incoming. So that might just be a response. It might just be, I just received something from someone, I'm going to gossip it to someone else. But then you look at this event right here, it doesn't actually have an other parent. So this might be this validator creating a transaction and broadcasting it to the network.
Okay, got it.
Okay. So yeah, node is an ancestor of another node. Then the next concept is strongly seeing. An event strongly sees another event if it can see events by greater than 2/3 of the other validators in the network, all that can see another event. So again, all of these are the same graph, just different colors to highlight different things. So if we just look at this one on the left, you can see the concept of strongly seeing. Yellow strongly sees orange because it can see red events by greater than 2/3 of the validators, which you can actually see it from all the validators. And all of these red events through these blue lines can be traced to the orange. So strongly seeing is it can see 2/3 of the events from other validators. All it can see an event.
Okay, so strongly seeing, so seeing is pretty straightforward, right? Like this event, somewhere recursively back through its graph, there's the other event. And strongly seeing is like this event, like I, as the validator who created this event, I know that other validators have events. I know that enough other validators have events that see some like previous generation of event.
Mm-hmm. Yeah, exactly. You can start to see the concept of like finality forming, or just like a complete view forming. Because not only do I know that an event exists, but now I know that the majority of the network knows that an event exists.
Yeah, okay.
And so they want that 2/3 for like some sort of fault tolerance, I'm assuming.
Yeah, exactly. The 2/3, you know, it can be equated pretty closely to Byzantine fault tolerance with the 2/3 threshold.
Cool.
So, what's up, Tomislav?
Hey, hi.
Hey.
Hello.
Jay's presenting his presentation on hashcraph.
Nice.
Yeah.
Yeah, just a quick run through. Yeah, so we're just defining some concepts. The one that we're on is witness. So an event is a witness if it can strongly see 2/3 of events, or if it can strongly see events by 2/3 of validators. So notice every definition is based on the last one. So a witness is an event that can not just strongly see some event, but it can strongly see events by 2/3 of other validators. So yellow is a witness here because of all four of these color-coded graphs show that it can strongly see some orange event, each one by a different validator. There's 4 total, which is greater than 2/3.
Yeah. Oh, yeah. I was going to ask, but I think I know the answer now. I was going to ask, it's okay. It makes sense to say like an event by validator by like Alice strongly sees a different event also by Alice. And I think that's what figure B is illustrating, actually.
I was going to ask the same question. Like, is it weird that you have to strongly see your own events through like 2/3 of the other validators? But I don't know. I guess that makes sense for some reason.
Yeah, that's a good point, actually. I guess what this tells you is that not only do you obviously know that your own event exists, but the majority of the other network knows that your own event exists.
Right. Yeah, and maybe that's the important part, is that you know other people know that it exists.
Because otherwise it seems like you shouldn't consider yourself.
Yeah, like clearly. Well, I don't know. I guess maybe not clearly because you can't equivocate, right? And pretend like you never saw your own event.
Yeah. But really, these concepts are not so much about equivocating as much as just finality. And because you know that you're a validator, an actor in the network, you know that you contribute to the finality of the group.
Mm-hmm.
So.
Okay, so witness was the one we were just on, right? And witness means an event is a witness if it sees, if it strongly sees, just like any event from 2/3 of the validators.
If it strongly sees, yeah, exactly.
For each validator in some 2/3 size subset of all the validators, it strongly sees an event from that validator.
Oh, yeah. It's not like events from a specific round or anything like that? Or is this all within one round, or rounds don't come in at all into this?
That's a good question. So the witnesses actually define the round.
Okay.
When you have a witness, it becomes round R+1.
Okay.
Oh, interesting. So when you have, so here we have a witness. It looks like probably that yellow one at the top is the first witness here.
Yeah.
Mm-hmm. Yeah.
So does that mean that like now for everybody, it's round R+1? I mean, I guess maybe not all of the validators would know that yet, but at least the middle column validator now knows like I'm on to the next round. So later, when there's enough events that like all of the validators have seen that yellow event, then it's also round R+1 for them, or they have to wait until they have a witness event themselves before entering the next round.
So an events round is based on its two parents. So it's the maximum of its two parents +1 if it's a witness. So if another event gets created above that has no relation to the witness as it already is, it would still be in the lower round.
Okay. Yeah, so it's not a question of like, is Bob in round 7? It's like, is this particular event in round 7?
Yeah, exactly.
Okay, got it.
Yeah, and it's not a temporal connection. It's more of a causal connection, I guess, is maybe the main point.
Yeah, definitely.
Is this somehow similar to these latest changes on ArcChain to have some alternation? I mean, this implies some kind of round. If you need to wait other validators to to get some stake from the network that you can include your block. Is this somehow related to rounds? Because you're forcing validators to alternate, what Greg was saying. Mm-hmm. So this somehow looks similar, because rounds, you're not creating a round, right?
I'm seeing the same problem with what do they call it, a rabbit here when you talk about the famous. And so how do they solve that problem? Yeah, I was anticipating that as well.
What'd you call it? A rabbit?
A rabbit. Yeah, he gets ahead, and then nobody else can ever catch up.
Yeah.
But in this case, you're not famous until you're strongly witnessed. So you're not going to be a rabbit. You're going to be with everybody else.
So it seems like it's you're famous in everybody else's eyes, but not your own eyes.
It's not always the problem.
Sounds like an identity crisis, right?
No, I mean, you could be famous in your own eyes just as much as everyone else's. I think it's really just up to what you can see. It could go either way.
So wait, what was famous about again?
Yeah, Jem anticipated it. It's that you're strongly witnessed by, or just that you're strongly witnessed. That's like the best definition I've ever heard, is 2 words.
Yeah.
But yeah, there's no visualization for it here, but it's just when greater than 2/3 witnesses of future rounds, usually R+1, can see an event from a previous round.
Okay, so to be famous, for an event to be famous, first of all, it has to be a witness, right? Or no, any event can be famous.
See, that's a fantastic question that nobody asked. That really gets into it. You have to be a witness to be famous. Yeah, though it doesn't really like tie to the definition, but in the implementation of hashcraph, that's how it works.
Okay. So
you sort of nudged us there, though, because you said that the concepts build on one another.
So like that yellow one at the top is a witness now, because it strongly sees some event from enough validators, more than 2/3.
Mm-hmm.
And so like we can imagine if this thing progressed, got a little taller, then eventually there'd be similar yellow witnesses in some of the other validators columns. And so then the witness becomes famous if when again?
So if this yellow event like pinged around all these others, and so they all got witnesses,
Mm-hmm.
then they would all see the same. They would in fact all strongly see the same events that this witness does. So that would make any event that this witness sees famous, because the majority of the validators' witnesses can all strongly see a previous event.
So wait, so when 2/3 of the validators have witness events that strongly see, say, this yellow one, then the yellow one is considered famous? Is that what you're saying?
Yeah, that would be true. Genesis events are also considered witnesses, so they can be famous too.
Okay. Oh, they're just witnesses by default, right?
Yeah.
Okay.
Just definition.
Yeah.
Can we relate famous with finalized?
Yeah, they're exactly the same thing.
Okay. Yeah, this makes sense.
And then finalized is recursive, right? So if some witness is found to be famous, then that means everything previously in its history, all of its parents and their parents are also finalized now.
All of its parents and other parents. Yeah. I mean, I'm wondering about this too. I think that is the case. So in the actual hashgraph algorithm, it's kind of interesting. You come to finality about witnesses themselves, and then once you have that, they actually use timestamps between to decide here the ordering. But I mean, the idea is still, I think that you should have a complete view of this graph once you've finalized the ends of a round. So I'm not totally sure why they use timestamping. It's something that I haven't looked too much into.
But this is not the real time step of the wall clock, right? This is just timestamp.
No, yeah, it's real timestamps. That's what confuses me. So I mean, that's what he says. He says that once we have this finalization above, then I think, you do have this concept of you have a complete view, and you know that everyone has a complete view. But for some reason, instead of just being able to say that it's now ordered, I guess the ordering comes in cases like which of these two, because in hashgraph you have a total ordering, not a partial ordering, even though it's a DAG. So this event right here and this event, you wouldn't know which one came first, even if you have the complete view. So I guess that's why they use timestamps.
Yeah, that's what I was thinking. Like the timestamps allow us to go from this partial ordering that hashgraph naturally gives us down to a total ordering, because like once we have this partial ordering, then we can use the timestamps to just like fill in those the comparisons. Like if we have a question like which one came earlier and the hashgraph partial ordering doesn't answer it, then we can fall back to like timestamp based ordering.
That's interesting, because hashcraph, the actual network uses the EVM, Ethereum Virtual Machine, which is a serial computer and something that you do need a total ordering on underneath. So I guess that kind of explains why they have this timestamping. But you still see that you can reach consensus in parallel on separate transactions at the same time and still get this total ordering, maybe at the sacrifice of some security for how timestamping works, but still you get this parallelism for free between rounds, which is interesting.
Yeah, I'm curious now, like if we just choose two events there that seem like they only have a partial ordering, and like if for some reason those, like perfect example. So like imagine if those were like calls to the same contract in such a way that like they don't commute for some reason, and they're both. Oh yeah, okay. So do the. Yeah, okay, so let me finish that thought. So like, let's say those two calls don't commute, and now because of the way the hash graph was built and like maybe that yellow witness at the top becomes famous, and so like all this stuff is finalized, then we still have this question to answer of which one came first, and that's something that people probably will really care about because those calls don't commute. So that seems like maybe a problem.
Yeah. Well, I mean, that's why they have the timestamping,
Yeah.
So without it, it's just a partial ordering, and you can't use, a virtual machine that isn't parallel like the Rovium.
Yeah. So, but I'm saying like, let's say, Jay, maybe on the left side, you made that transaction thinking the state of whatever contract was one thing, and then at around the same time, I made that transaction in the right column to the same contract thinking I had the same exact starting state you did. And now definitely one of us is going to be making a call that we didn't intend to make because like, let's say yours goes in first. I now made a call into a contract whose starting state was not what I thought it was. So like, I see how the timestamps allow us to get a total ordering, but then the problem is like, oh man, I just made this call to a contract who I wouldn't have made that call if I clearly understood what its state was going to be.
Gotcha. Yeah, that's totally true. Yeah. So you one has to win and the other not.
Yeah. I'm curious if like when I deploy or like when both of us, when anyone deploys their contract, they get to like somehow say like this is only valid in such a state or something like that. I don't know the EVM well enough to know if that's like a reasonably simple thing to describe.
Yeah, and it might also just be done at the hashgraph level. If you have this concept of finalization that only happens, once a round is complete and the next round is complete also, then, once you have all these events, you could say, all right, here's the total ordering. This event doesn't commute with this one, and this one actually came first, so we're just going to use that for the actual state transition and ignore the other one.
Yeah.
This seems like a second level of consensus in Casanova, right? You have this ordering on the first level. If you don't have conflicts, everything works. But if you have this kind of this is like a conflict, and in that case, you are doing this another level of consensus because you want to have a total ordering inside the block, right? Inside this run, right?
Yeah, that makes sense. I guess the tricky part is then how do you decide, like in a model like the EVM, how do you decide what things conflict? Because Casanova was really careful. Well, at least Casanova just said like you have to have these conflict domains, and then C Delta was careful to say like here are the conflict domains. It depends what pub key is spending funds. But with EVM, that seems kind of tricky. Or maybe just calls to the same contract address conflict or something. Maybe it's not.
Yeah, and how this is reflected to this ordering, right? This is only when you're doing something that it's exactly like in your example, you are depending on some ordering Yeah, and how can you detect this? Yeah. Maybe it's not so complicated. Maybe you're just trying to change the same part of the memory, or the state. I'm not sure how this works in EVM.
Yeah, I mean, I could definitely see this like DAG view being, almost serialized. Like you interpret it once you know the total ordering, you pull out the transactions that are inconvenient for the network or that are incompatible, and you build basically what looks like a normal. You could basically serialize the hashcraph block tag into the Ethereum blockchain.
Yeah, but Jay, the crux there was that you said like you pull out the ones that conflict or that don't work together, but then the hard part is how do you know which ones that is? How do you know which ones conflict?
Couldn't you just use? Oh, okay. Yeah, I see what you're saying. Well, I mean, if you run through it like you do a transaction pool or something like that, and you take the first event that runs through the network.
I'm thinking one way to do it would be like an O of n squared, like try to apply these transactions in every, or no, that's exponential time, I guess, like try to apply them in every possible order. And if you get the same post state, like for any order, then they all commute. And if not, then I don't know what you do.
Is there not like a greedy algorithm or something where you could just like pull the latest one and then pull the next latest one?
Yeah, and maybe then you can use this timestamp and some kind of logic that you can decide and say, okay, this conflicts, but it's later after this one, so this first one will win, and I don't know what to do with this later. Maybe put it in another block. But yeah, if this is conflicting, it's like an orphan, right?
Yeah.
Yeah.
So what relation do the rounds have to the blocks in hashgraph?
Rounds are really just useful, for determining finality, and then, well, they don't really have a concept of finality, I guess. Rounds are mostly just useful, I think, for kind of internal caching, I guess, is the main thing. Is that once you have this concept of a round, you know which events you need to store in memory in order to reason about finality or witnesses, things like that. Because you don't really need to track more than like 2 generations past if everything is going according to plan.
And rounds are created with the messages, with the gossip messages on the network, right? When you receive enough messages, you really create another round, right? And this is like for each validator, right?
Yeah. Once you have a witness, which is basically like receiving enough messages, then once you have a witness, you have built up a strong enough vision of the view underneath you, and you call that a round.
I'm under impression of this presentation from this guy Hoffman, and related to error correcting codes, right? Now it makes more sense that you are sending messages and you want to receive all of these corrections so that you can go to the next step, right? So you don't want to some validators that fall behind, or some validators that are like rabbits and go further without all of these corrections from other validators. They're giving you some kind of constraint and like a balance the network.
So are you saying that hashgraph, these witnesses give you that constraint, or that they don't?
Yeah. This constraint that you need to wait some messages from other validators, because now I see that this is very similar to what Greg was explaining now in Archen and Casper, right? If validator wants to create a new block, validator must first find or wait to 1/3 of, and this 1/3 is just like first try or approximation to make it work, right? So you wait some amount of stake from the network. You must this stake include in your next block. So if you don't see other messages from other validators, their blocks, you cannot publish your own block. You must wait. And now there is some kind of bug, and all the validators are just waiting for new messages. So there is some kind of problem. But this seems very similar to rounds. You are forcing rounds. And Greg was saying that this kind of this first algorithm they are now implemented, it's not constraining to any specific rounding algorithm, right? It's not, forcing some kind of round robin or anything else. But there is some kind of notion of rounds, right?
So this is the first I've heard of the rabbit thing, but let me just see if I picked it up correctly. So the idea is like, if we're all validators here and I happen to make a block and send it around to you guys, then like since I'm the one who made it, I was the first one who got to know about the block, and I like already validated it and everything before I even sent it to you guys. And so now I have a head start on making the next block.
Yeah.
So while you're like busy validating my block, I already have another one up my sleeve and I send it out.
Yeah.
So what, is there any reason, if you guys notice that's happening, that I'm like starting to go just 3, 4, 5 blocks in a row, is there any reason you have to build on those? Or like, what if you're just like, oh man, screw this guy, I'm sick of including all his blocks, like I'm just going to make my own, and yeah, hopefully that'll orphan some of his off. And
yeah, each validator can create their own DAG, right? But yeah, this is like a partitioning on the network also.
Yeah, that's right.
And they talk about this. What if really you are disconnected? So this happens all the time, right?
Yeah.
And you don't have any other. You don't see any other validators. So you need to create another block. And I think Steve explained this to me when there will be some kind of partial slashing. So you will be slashed, but later if other validators find out that your network was just, you're not like on purpose, you're something try to do to the network. So yeah, then you will receive back your stake that you're slashed. So this seems like a pretty complicated to detect, and or you're just playing with your network connection and just you're saying, oh, my network is not working, so I just created this 1,000 blocks. So
yeah, I just made all these blocks while I was rebooting my router. Good luck.
Yeah.
So what was the solution that our chain came up with? Like, you can't just make a block whenever you feel like it. You have to do something different.
You can't use a block you've created as justification.
Oh, that's how the alternation is enforced.
Yeah.
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 So somebody else has to.
Oh.
So you need to include hashes for a parent for your block. You need to include hashes of the blocks from other validators than you that have a stake 1/3 on 1/2. I'm not sure what will be the exact number, and maybe in the future this will be like a dynamic thing. So you can automatically configure this number to tweak the network.
Wait, so you have to be justified by someone that has 1/3 of the stake in the whole network?
But other people who sum to 1/3, maybe.
Yeah.
Yeah, other validators.
And that's for every like what's the word? Every chain, or every spin-off, like every thread in the DAG.
Yeah, for each block. And this is like, I think it's very, very similar to this strongly C, because you are waiting, before your next block, you are waiting messages from 1/3 that you can just create another block. This is not like finalized. This is just, right? Some kind of another round. You're starting another round.
Yeah, it's not finalized yet. Yeah, it's just a round.
Yeah.
And what's interesting, they thought having that 1/3 stake was going to be the solution, but apparently it didn't solve the issue. So they increased it to 51%. And at 51%, you get a lot of rejections, blocks that are thrown away. So the performance has increased, but now you have all these blocks that are thrown to the side, actually 80%. So what Sebastian is working on is tagging all of these rejections to identify why are these blocks being thrown away. So in the end, there's going to be the solution will be a combination. It'll be somewhere 51%, maybe down to 1/3. But then you get the performance, but then you got to modulate it due to all of these blocks that are being thrown away. So they don't have the exact answer yet, but they're slowly zeroing in on it.
So this might be a stupid question, but why is it a problem if one validator is making all or the majority of the blocks? What bad thing happens then?
So Greg was saying that the network is not live anymore.
And reliableness relates to that social ability. You want all of the validators working together with one another, communicating. So if you have one validator who's creating the blocks and using itself to justify, and then moving on and using itself once again to justify, it's siloed off, and that by definition that's not the liveness that you want, and that causes that rabbiting effect. It can move ahead faster than the others. So when you have liveness, you have fairness, and everyone's playing equally, and you have less of a chance of validators falling behind.
Right. What we're getting is long proposed times. Okay, proposed times go through the roof.
Right. So
after what, 2,000
blocks.
So that long proposed times, like, is our chain specific lingo that means like a particular validator isn't able to get their block out, right? So that's the same symptom you described, where like I can't get my block in because some rabbit is making all the other blocks. But as long as everybody else is validating them and we're still reaching safety like the normal Casper way, I'm not sure why that's a problem. Or is it maybe because like block rewards mint tokens or something and they all go to the same validator?
Well, also,
they're not reaching any consensus.
Yeah.
So,
and if another validator then wants to justify a rabbit, then he would have to justify all of his previous blocks, right? So it's like if one person is running on a supercomputer, then all of a sudden no one in the network could ever catch up to him, and they might all stop even participating in the network because they're working on validating his blocks.
But I see Josh's point that you have this one chain from this one rabbit, right? But you can, other validators can create on like their own DAG and just in one moment merge with this rabbit, or this makes sense, right?
Just that the merging, you have to validate everything that the rabbit has done. So
because this rabbit will doesn't have this amount of stake like other validators. They, right?
Well, we don't know. You know, it could be a validator that has a large stake, or it could be a validator that has a minimal stake. And in in those scenarios, now you have a validator who has a very small stake, but kind of who's leading doing all of the processing, all of the validating, and that you don't want.
Oh. Yeah, so I guess like in Casper, I'm just remembering like in Casper, the way you vote on other people's blocks is by making your own blocks. So like I like implicitly vote on Alice's block by like citing it in the justification of my block. So I guess if I can't get my blocks out, then I can't vote for anyone else's, including the rabbits, and like so then we never get finality on those blocks, and that's the liveness issue.
Yeah, but how this one validator, if he doesn't have more than 2/3 of the stake, other validators can build on other blocks other than this rabbit blocks that are just self-justified, right? Because all of these blocks in this rabbit chain, they will have the same stake. For whatever, how many blocks do you create, right?
Yeah, right.
You will not gain anything for creating blocks. Yeah, this is like strange. Yeah.
Maybe the maybe the real bug is that the software just like prioritizes validating blocks over anything else. So like maybe the rational choice is like, oh wow, I see, you know, Rabbit Validator has this super long chain all by themselves, but like I'm going to irrationally not build on the part that I can keep up with and instead just try to validate that long chain.
Yeah, because your block will be fine if you send it to other validators, right? Other validators will say, okay, this is valid block. It's built on more than 2/3 of stake, and
yeah. But then you're basically just kicking him off the network.
Yeah, which is fine. You know, you're creating blocks like crazy.
Yeah, the squishy social consensus is to slow down so we can keep up, or else you don't get to play no more.
Yeah, this is interesting. I feel like this is like I don't know, like a libertarian view or something. It's like let the consensus market evolve on its own.
Yeah.
Yeah, but wasn't it that the turtles also tried to get a consensus, you know, and the rabbit going for one consensus and the turtles going for the other consensus, or the rabbit was making it so that nobody had a 2/3 of the stake, and no block could be validated or finalized.
Yeah, it seems like that would only be a problem if the rabbit had more than a third of the stake. But if that's the case, then you're already in dangerous waters, because if that rabbit is Byzantine, then they already violated your 2/3 honest majority assumption.
Yeah. And this is exactly definition to that you can prevent liveness if you have 1/3 of it, right? Yeah, and Josh, you said that maybe validators just trying to validate this this rabbit without first looking at what can they already publish. So yeah, this makes sense.
Yeah, I'm curious though if that proposal to include enough other weight in your justification, that seems like an interesting idea too.
Yep.
One question I've got about hashcraph is my understanding is that some part of hashcraph is patented.
Yeah, the actual algorithm is
The actual what?
the consensus algorithm. The whole thing is an IP patent.
But they say that open source something. So is this still under patent or something is?
Yeah, and they're
think
going to open source it, but it's still going to be patented. So you know, it won't be under like an open license or anything. It won't be free use.
This is what Richard Stallman always complains about and why he hates the term open source, right? Because the source code is there for you to view, but you still can't use it without paying the money or whatever.
Yeah. Yeah, I do, you know, wonder, like, I shouldn't even talk about this on the recording, but like...
We can stop the recording if you want. Jim, would it be all right to stop the recording for...
That's interesting. That'd be pretty cool. I'm imagining almost like a marketplace of consensus algorithms, and you have like a single platform, and you just go shop like, hey, I want to open up a new namespace for my photos that I want to store on the cloud. And photos.
Maybe you want to, you know, you have more trusted customers. So you will for them you will run some kind of more not so strict consensus algorithm, right? Because they are trusted, and you know you have some benefits. And
yeah, but this is also something that you could run on like what is it? Filecoin or what's the other one? Can't remember right now.
Filecoin, IPFS or Keybase?
Yeah, it's like a layer on top of IPFS where you can pay people to store your files. Another one is storage, I think. It's a fantastic idea. You know, it's like Airbnb for hard drives. Man, I can't think of the main one right now. It's killing me. But yeah, I mean, that idea is fantastic. But yeah, it would be very interesting if you could add a layer of consensus on top of that, so that not only are your photos and storage distributed among, you know, computers everywhere, but you actually also have a complete view and idea of what your current photos are, and all those nodes are reaching consensus together.
Yeah. And we are now thinking about file systems, but if we have like a tuple space with a rolling on top of that, I'm not sure that we need a file system. You know,
Well, you're not sure we need a file system on our chain?
Yeah. Because you can easily store whatever you want. So. Yeah. Why should you just think about this old idea of, you know, directories and files, and they don't have a structure that rich as a rolling. So it's difficult to search. It's difficult. Everything is difficult because the structure is very simple. You just have like simple trees,
and that's the tuple space.
Yeah, with the tuple space, you have many different options. It's a language. It's not just simple structure. It's very rich structure, so you can do much richer thing. If you want to link files, it's very strange. You have hard links, symbolic links, and on one system this works one way, on another system different way. And how can you write consensus in this style? It's difficult.
Yeah, and that brings up the issue of Rolang being a database query language. So it would be querying on the tuple space, essentially. Is that what the thought is?
Yeah, and search on a tuple space. But what this means? This means search Rolang source code. Okay. Because you are searching on a higher level with the Rolang language. But what is stored in tuple space is exactly the source code.
Yeah, so Tomislav, that makes sense I guess the tricky part to me though is like at some point all of that information still has to be written as bits onto a disk somewhere, right? And so like what is the incentivization mechanism for someone to have all that disk? You know, like why if I'm a validator and someone just dumps some huge file and I happen to notice they don't query it very much, like why would I keep that on my disk?
Oh, you mean you're paid for storing the file, and you are saying everyone that I have this file.
Oh, that's okay. That's what you're talking about. I thought for a second you were saying like that sort of system wasn't necessary because Rolang has this rich structure that mixes the querying with the data.
Oh, no. I'm saying that on the layer of defining what we are now calling a file system, because you have just sequence of bytes on your SSD. So what kind of format you will use to store this data? Now we are using in Arnode, they are using LMDB, right?
Yeah.
So LMDB is this kind of bridge between abstract representation in tuple space to something that we call file system. But if we skip LMDB and we can just store it on the drive directly in some way. I'm not sure what is the how can just skip LMDB and
So what is LMDB exactly?
It's a key value store. Like they say they're a little better than this very popular
Like CouchDB or something?
Light DB or
yeah.
I'm not sure.
It's the old
Facebook have
Berkeley DB.
So the keys. So the keys are the tuples, the names of the tuples, and the values are the location in your actual file system where it's stored. Is that the idea?
The keys are the channels in send or receive. They are exactly the names, and the values are also the processes. For a send is the process that you're sending, and for receive it's continuation.
Gotcha.
So this is why Greg is saying that keys are names, and the values can be or the data or the continuation.
Yeah.
Yeah, and the LMDB lets you do most of everything in memory.
Yeah, they're using some kind of hashes to. I think that Isaac can say more about how can you store processes in this structure like multiset, and then you can just query it somehow or take a hash and then search for a hash. I'm not sure how exactly this works. I would like to know.
Wait, sorry, what was the context? I missed the first part of the question. So
how they're storing names as the keys, but they're not storing exactly the source code. They're storing like hashes of this code, and they know that this exact hash is the same when they're searching. Although you have some kind of variables, bound variables, so you must implement some kind of alpha equivalence and structural equivalence and.
Yeah, so you're asking how they're actually doing the implementation for RSpace?
Yeah, especially if you have multiple binds, and it's not easy to create a structure that you can just hash and say, okay, they are the same, because you have different permutations. So you have different hashes that are like correct and the same. So are they storing these different hashes, and they say, okay, one of these is okay, if you have.
That's a really hard problem. That's the spot where I struggled the most when I was trying to do JS Roxy. But like I think one key observation is that you never have to use a channel as a key until it's fully concrete. You won't have just a like an unbound, you can't have an unbound variable as your channel. So even if your channel is something complicated, composed of lots of variables, those all have to be bound to something. So then once you normalize it, then you can hash it.
Yeah. Oh yeah. Yeah. You definitely search for this normal form, right?
Yeah, right, exactly.
And you're saying without free variables.
And the point of the normalization, right, is to just have that unique representation.
Yeah. Yeah, so then like there's like one question that I went back and forth on a lot is like, you know, maybe when I'm writing my code, there's like really deep in continuations of continuations, there's like some send, you know, a channel that's composed of like a bunch of variables, and then I just send some data on it. But when that first goes into the tuple space, that's not a key yet. That's going to be on the value side. That's the like that, you know, it's in continuations of continuations. So that very top level continuation is data. It goes on the value side. And it's not until you've made a bunch of reductions that that send finally gets executed. And by the time you've done that, all those variables are bound. So then you have a totally concrete thing to hash and put in your key value store.
Yeah. Yeah. And yeah, when you create a new deploy, it must be without free variables, right?
Yeah, the whole deploy, it's the like top level term must be without free variables. Yeah.
Oh yeah. This is exactly top level term. Yeah.
And that's all. And when you do a deploy, that's all you're doing is putting in one top level term.
Yeah. Another part
paired together. Yeah.
Yeah. Yeah. I was talking to Jay, and I was realized that you are putting all of the tuple space existing in our node with your small in par with your small deploy, right? But they're merging. They're the same. They're not different, right? You're just merging these two deploys. This one is big, and this your is very small.
Yeah.
It's very simple concept here, right?
So I don't know if you guys want to switch topics a little bit. I do have some new developments in K. We don't have to go there right this second.
Yeah, I'm down. I'd like to see it. I haven't seen your K framework work in a long time.
Yeah, I figured out all of the multiple like listen receive matching business. Like I have, you know, everything is 100% working there, like exactly the way that I want it, except for a small thing that I want to change.